Okay, lecture 28. So this will be another short lecture. Then what we'll do is spend the rest of the time talking about exam 2. Any last minute questions you guys have. We can go over the practice exam too. Of course we won't have enough time to go over the whole thing, but there may be some particular questions you guys have about exam 2 practice. So for review, on lecture 26, we went over the small signal parameter comparison between the transistors. And right here, so we looked at these various parameters right here, and for the bipolar and the FETs right here. We also looked at the common emitter, common source amplifier characteristics right here, parameters, and common emitter amplifier, common source amplifiers. We also looked at power for the drain and source of these MOSFETs and BJTs right there. And for lecture 27, we looked at the various kinds of ports, and we found out that for the BJTs, it's actually the same for the FETs too. So the inputs for the base and the gate those are good places for inputs. Also for the emitter and also the source right here. And for outputs, good places for those are the collector and emitter and the drain and the source. We also looked at different families. We looked at these two last time, and for now we'll start here, looking at common base and common gate. Okay, so we're going to take care of this section right here of chapter 14. Okay, so in terms of common, recall when we talk about common, we're talking about the common connections between the input and output ports, and also other things. Okay, so right here we have the common emitter and common source right here, and those are common to the input and output. Right here we have the common collector, common drain, right here and here, and they're grounded, so it's really the same reference as the output and input for those two. And now we're going to look at the common base and common gate, and those are also common to the inputs and outputs. And how we made these common, typically we used an AC bypass, right? So for the small signal analysis, capacitors, they look like short circuits, so we're able to make those common grounds. And for certain things like the common emitter, we were able to go through this right here. So it's still a reference to this ground right here, but that's the common emitter right there. It goes through this RE, and this right here goes through RS, but still same reference. Okay, so let's look at the third class right here, this third class right here. Okay, so this is the common base and common gain amplifiers, common base and common gain. So they typically look like this right here, and these are the versions that you get when you take into account your small signal analysis. Okay, and you can clearly see here, after you do all that, you do end up with this base being in common, and also the gate being in common with the inputs and outputs. Okay, and what happens is that this load right here, that is this R3 in parallel with RC up here, where that becomes ground. So here's your starting node, and then they both go to ground right there. So that is in parallel with that, and that gets short-circuited. Over here, it's very similar, where you have this RD being in parallel with R3, where that is grounded and this becomes short-circuited. Okay, so that's where those things come from. Okay, so the AC signals are injected into the emitter or the source. Okay, so we're talking right here, right here, and extracted from the collector or drain. So being extracted from the collector or the drain. And you can see that because here's the voltages right here, right? So that's where that signal is coming from. The base and the gate terminals right here are connected to signal ground through the bypass capacitors, and you can see that where this base right here is connected to this ground through this bypass capacitor right here. Okay, And this gate, same thing, is connected to the ground through this bypass capacitor. And remember, it's only for AC, small signal AC signals, okay? Okay, so where was I? And so, yeah, so these terminals right there, those are the common connections between the input and output ports. And as you can see, these AC equivalent circuits are identical in structure, even though this is a bipolar and that's a FET. Okay, but otherwise, same kind of structure for both of those for AC analysis. All right, so let's do a quick review on this slide right here, a small signal. So remember, this is what we have for the BJTs. This is what we have for the MOSFETs. And they're pretty much identical. The only difference is that instead of this being an open circuit, we have this input resistance right here. Okay, but if you let that go to infinity, then you end up with this over there. Okay, so here's just small signal parameters at the Q point. Okay, so we have the transconductance, we have the input resistance, output resistance. This beta 0 is the current gain, and this is the intrinsic gain right here, voltage gain, the mu f. And this is for the BJTs, this is for the MOSFETs. Remember, this value for the intrinsic gain, this is pretty constant because that early voltage is constant. And also, well, there are pros and cons, and we went through a lot of these. Oh yeah, but keep in mind, this input resistance and this output resistance, these correspond to the transistor only, not to the other resistors that surround them. So if you want to find the overall input and overall output, you have to look from whatever input you're considering as input and whatever output you're considering as output. Okay, but this R pi and R0, that's just for the around the transistor itself. Okay, so let's look at the common emitter amplifier. Okay, and so this is what we have for the common emitter amplifier, and this part right here is seen as Rn. Okay, at this amplifier right there. And so to go from here to here, we use the AC equivalent. Okay, so we just talked about this. This becomes the AC bypass. And so all that's left is you have this emitter right here, and it just goes through the RE, and then you have this virtual AC ground, which is right here. Okay. Here's the R out seen from this capacitor. Okay. Now this right here, this goes through R3, but R3, like we just said before, is in parallel with this RC because that's going to be grounded. That's where you see these two together like that. That's why those are in parallel. And since this is also going to ground, but it's starting at a different node, it is in parallel with this one going to ground. Okay, so your R1 is in parallel with R2. And that's what that is right here. We're going to call this RB. Okay. And this resistor right here, this resistor is like part of the input. So you have your input source, that voltage, and your source has some kind of resistance as well. And oh yeah, so this capacitor right here, this C3, that's the part that forms the common reference connection between the emitter right here and the input and the output. So common emitter. Okay, so that's the first stage, going from the common emitter amplifier to the AC equivalent circuit. The next stage is going from AC equivalent circuit to the small signal model. Okay, so what we do here is we take this BJT and we replace it with a voltage controlled current source. Okay, and also in there you have your R0, so it has some R0 looking into that, your output. And that's what that is right there. Everything else is the same. You still have your RC and R3 in parallel right here. And you still have this RB, which was the R1 and R2 in parallel. That's the RB. And you still have the input resistance from your source. Okay. And then, so once you have that, then you can go from that to this, even a more simplified model. And that is if you can neglect this R0, okay? And so one way to neglect it is if you're going to assume that your voltage gain, beta F, is much, much less than your intrinsic voltage gain, the mu F. So if that's the case, and that's a good assumption to make, then you can get rid of this resistor right here. So that's why it's gone over here. And this right here, the RC being parallel with R3, that becomes your load. Remember, they're at the same voltage as right here, so it's still fine. So that's what this RL is those two in parallel. Okay. Now, if you can't neglect that, then here's some approximations that you can make for R0. It could be your early voltage over your IC, your collector current, or it could be this 1 over lambda RD if you're looking at the FETs. Okay, so now the emitter portion of the circuit represents the common connection between the amplifier and the input ports. So that's what this is right here. And the input signal is applied to the transistor base right here. It's being applied to this. So here's like the input signal, and that's where the base is, B. And the output signal appears at the collector, okay? And both input and output signals are a reference to the common emitter terminal through RE. Okay, so the output is like from your collector, and the input is for the base, and then you have your emitter, and that goes through your RE, and that's how they're all related to, they're all common right there. And so these right here are going to be these right here, okay, where you have your voltage VB, your voltage right here, your VC at your collector, and your voltage E right here for your emitter. Okay. And then, so if you want to look for your terminal voltage gain, okay, and that's this right here. So now the overall gain from the signal source VI to the output VO across this RL over here, that's just this gain right here for the whole thing. And that's just the overall output voltage right here divided by the overall input right there. Okay, but you can separate these two out. So VO, wait a minute. Okay, so so VO right here is equal to VC. Okay, right? So this VO and this VI can go from here to here. So that's really VO right there. And then you insert your VB, this other voltage right there. And then so this piece right here becomes your terminal gain, what you're looking for. So that's the VC over VB. And here's the other thing right there. Now your collector current, your collector voltage right here, that can be described as this IB times beta 0 multiplied by RL. And that's what we have right here. So this right here can be this, which is your transconductance GM times your voltage between your base and your emitter. You could rewrite that instead of a voltage-controlled current source, you could rewrite it as a current-controlled current source by using your current gain. And your current gain, beta 0, is just your GM VB over IB. And this VB over IB is really like your R pi, right? You can see that right here. Here's VB, here's IB, and that's the ratio of that, R pi. Okay, so that's what this is right there. And so if you have this current going from 0 through this direction right here, the voltage here is going to be negative. Okay, so that's where the negative comes from. And this negative also means that you're going to be 180 degrees out of phase once you get done with it, unless you have another negative, but that's the only one. So that's where this comes from, right here. And Supposed to be E right here. Base. Um, your base voltage is VB, and it's these values right there. So one way to get your base your base voltage, you can do like a loop around here, right? So so for example, you have some current going through here. So here's your VB, and remember, so going from this circuit to this circuit right here, this VB, you're making like a simplification where this is the voltage that you're really concerned about. So you group all this together, you lump all this together and just put it in here and just say, well, that's your VB you're concerned about right here. Okay? And your RIB is your resistance looking at it from this point on this direction. Okay? So that's what this is. Okay? So you're no longer really considering these resistors right here because they're like, tied in there. So your current going through here is your IB, okay? And that's going through downhill through that R pi. So there's a voltage drop. That's what this is right here. And then through this resistor, this RE, you have this current right here, which is the beta IB, and then you have this IB, and they're all going through right here. So that's where this comes from. Your IB plus your beta IB, and they're being multiplied by that resistance. So it's like the sum of those currents going through there. So this is just done by your KVL, okay? And so your terminal gain is your VC over VB. Here's your VC, here's your VB. You plug those in here, and this is what you get. Well, this is what you get right here. So you do have your 180 degrees out of phase. And if you assume your current gain is much, much greater than 1, then you can forget about that one right there. And also you can assume that, that this beta is equal to the transconductance times the input resistance. Yeah, I think that's where this, that's where the GMs are coming from, right there. Okay. So, anyways, so this is your approximation right here for the terminal gain, and the last thing we're going to talk about is your input resistance and overall input resistance. So, your input resistance is looking into the base. That's this RIB right here. And here's another way of looking at it down here. This is even a greater simplification. Okay, now that's the ratio of your VB to IB. This right there. So VB to IB, your VB from this piece right here, we did this by KVL around this loop here. That's what this is. Plug all this into there, and the nice thing about that is that you have all these IBs in there, right? So they all go away, and this is all you're left with. And if you replace your beta 0 with this GM R pi, right? And then you can also assume that your current gain is much, much greater than 1, and then you end up with this expression right here. Okay, so that's what our IB is. And again, RIB is looking at it from this point on, from your VB, or right here, or looking at it from right here, that direction. Now your overall input resistance, this Rn, that's the resistance looking into the amplifier at the coupling capacitor right here. So here's a coupling capacitor. Here's another coupler, but and that's for R out. And we'll look at that next lecture. But for this right here, this is really like RB being in parallel with RIB. Okay? So remember, RB were these two in parallel, the R1 and R2, right? Because remember, that went to ground, So this one folded around and it was in parallel with R. So this R2 is in parallel with R1. That's from this point. From this point on, you have this RIB looking at it in that direction, and we just figured out, what that is right here. So from outside looking in, it looks like these two, which are in parallel to each other, that's in parallel with this RIB going to ground. Okay. All right, any questions about this stuff? All right, so since we have time, let's look at, I posted the solutions to the exam, the practice exam online. Exam. Oh, I only got 100%, not 120. Okay, so you guys need to see this. Duplicate. Okay. So, I just did that this morning, so I don't know if you guys had a chance to look at this yet, if you didn't view the video. So first off, are there any questions about problem number 1? You guys good with problem number 1 now? Okay. What about I'm not sure if I made this clear in the video or not, but okay, see that statement right there where it says assume that the ROs are not negligible? That's these guys right here. Okay, if they were negligible, meaning that if they were like really small valued, that means that this right here is very small, much smaller than that. So the whole denominator just becomes like Ri3. Same here. Then what you get is like this ratio becomes 1, and that ratio becomes 1. So the overall gain is just A3, A2, and A1 alone, without the resistors. Okay, so what about number 2? Any questions about that? Okay, so do you see how, so these are just the y parameters, okay? And the y parameters are just from KCL, okay? And they're in terms of the outside things, right? So you have like, the things you control from the outside are sensed from your outside. You have the currents and voltages. And so you have the currents and they're in a linear combination with the voltages, V1 and V2. Okay. Now, what we have for one of these stages, which is what this is talking about right there, the stage looks like this, right? And so what I did, I put the stage and I converted it to this. So this is Thevenin form, and this is just Norton form. Okay. So to go back and forth, the resistances are the same, but for the voltage, for the current, you just convert them to using the resistor. So this is in terms of voltage. To make that in terms of a current, you just divide it by the resistance. If you went the other direction, and that was in terms of a current, then you just multiply by R to get the voltage. Okay, and that would be your new voltage. And then looking at it from the outside, you can't tell if the inside of that black box is a Thevenin or Norton. They behave exactly the same. Okay, but once it's in this form, then you can clearly see what these what the conductance matrix must be. So you can clearly see here that G1 must be 0, and so forth. And this right here is your G2 from that. Oh, and that's because it's going in the opposite direction. That's like positive sense going down. This is positive sense going upwards like that. So you guys okay with that one? Alrighty. Number 3. Okay, yeah, so this one had to do with beta. You know, we had a little problem because in lecture I was like, oh, this is going to, beta is going to be R2 over R1, R3. You know, so I had those backwards, and then someone corrected me. So, this is a good way, I think, to think about beta. Okay, so if you're looking at a system like this right here, where you have the thing you're really worried about is this piece right here. And you have a R2 on top and an R1 right here. So remember how we first were introduced to beta. We're here you have your gain A, your gain beta. And it was a positive, it was negative feedback. And negative feedback, what that meant was that that part was minus, not plus. So plus and minus. So your feedback was minus. So whatever this is, it goes through this. So like if this is your V out, then what comes out of here is your beta V out, going up, you know, that direction. And what, okay, so anyway, so that's what's happening here. And this piece right here, think of this as your summer, which is a difference, right? Okay, so you have these two signals coming in here. You're combining them together, and then you're going through some amplification right here to your V out, and then you're going back this way. So this right here is like your beta. Okay, so if that's your beta, here's the input to the beta, here's the output to the beta, right? And so if you do your beta, S gain is V out over V in. And so if you look at your V out here, you could do voltage division. So if you do your voltage division, you'll see that's R1 over R1 plus R2 multiplied by whatever Vn is. And then that's why for this you have your R1 over R1 plus R2 for your beta. And you could do a similar argument for the other circuit right here, where you have that kind of feedback loop, where here's the input going in this direction, and here's the output right here. And here's your, I guess, summer and your A. And all this right here, that's your beta. So that's 3 and 4. So R3, R4. So for your V out, if you do, again, your voltage division, you have R3 divided by R3 plus R4 multiply by your input. And the ratio of that is just this piece right here. So this is the beta. Okay. Oh, yeah, so for the when you do your T and your feedback, you turn off your sources. So yeah, if you had like a source right here, you turn it off, and that's like the kind of ground kind of thing. Yeah, it's kind of weird to look at it as Well, yeah, okay. But, okay, so yeah, so that's that part. And another thing you want to be careful about is the difference between A and A ideal. Okay, A should be called like A non-ideal. A non-ideal are these guys. Okay, so like if you have an amplifier and it's giving you this value, assume it's a non-ideal amplifier. Okay, so the real amplification is A1. The real amplification here is A2, and it could be like 10,000, I don't know, 5,000, whatever. That's what goes right here. This A ideal, that's what this is, right? For this kind of structure, if it was ideal, where these two things were, there's no voltage difference between those two, no current going in, and all that good stuff. Then it's 1 plus your feedback right here over your R1. This one right here would be negative of your feedback over this R3. And then, so those two things go here and here. And then what goes for your nonlinear right here, for your loop gain, are these nonlinear A1s and A2s. Okay. Any more questions with that one? Okay. So for this one, oh yeah, so it said maximally flat, so you know what Q it is. And then due to the number of equations that we have, the only ones that are useful are these two. So that means you have to reduce your number of unknowns to just 2. But you have 3 unknowns. You have your R1, R2, and also C2 is also unknown. So you sort of constrain your system. There's nothing wrong with doing that. You can let R1 equal R2. If you wanted to, you could have said R1 equals 3 R2. It's as long as you state it somewhere. I mean, it's your circuit. But whatever that is, what's going to happen is that whatever those things are, that's going to, in order to meet these other constraints of omega and Q being 1 over square root of 2, your C2 is going to change because of that. So there's a wide variety of, there's like a continuum of values that you'll get a Q of that and a frequency of this. Okay, it's not unique to any one particular set of values. So you have lots of freedom. But yeah, you have your once you do that, then you finally have 2 equations, 2 unknowns, and then it becomes solvable. Okay. Oh, any more questions about this one right here? Anyone? Cinco. Okay, so for this one right here, you have your switch capacitors, and on Sunday we found out that this current is really going this direction. So that means that that positive sense is wrong. But if that's a positive sense, that means that means you know that your current is really, it has to be negative. That's the right sense for the actual current. So that current's going to be positive. Okay. Also, because the voltage here, since that voltage is 0, and you're starting at some voltage and you're going downhill to get to 0, that means you have to start at a higher value than 0 to get down to 0. So that's how you know that your voltage here is positive. Okay, so that means this is a non-inverter. It's not going to invert your signal. But in this case, that's negative. That's 0. Then you're going downhill from that, so that's going to be lower than 0. So it's going to be negative. So that voltage is going to be negative. So that's an inverter. Okay. So any questions about this? I mean, what's really cool about these kind of circuits right here is because you could just change the sequence of these things. These two are the same circuits, right? But you could change the sequence of how switch 1 and 2 are operating, and you can turn it into an inverter or a non-inverter. Just by changing the timing, which is really cool. Okay. For this one, I guess this is like one of these inspection kind of problems where you're given something in 3-bit, and then you figure out the kind of elements you have for 3-bit. So yeah, so for this 3-bit, you found out that the number of resistors were 8. These are 8 of those. And then you see how that corresponds to the number of bits, which is 3. So it's like, that nicely is like 2 to the third, right? But for the comparators, there's 7 of those. So that's like 8 minus 1. So 2 to the third is minus 1. And so for 4-bit, if that's the right formula, then you just plug in 4 instead of 3. And you could do the same thing with higher bits or lower bits. Okay, so for number 7, so this is one of these oscillator type of problems, right? And you're going to use the Barkhausen criterion, which is for oscillation that the gain of the of this loop gain right here has to be 1. I'm sorry, the magnitude of this has to be 1, and the angle of t has to be 0 degrees or 360. Okay. So it's given to you. Thank goodness. So you have to calculate it. Now the S, that's j omega, so this is a complex number here and here. So it's just rewritten right here. So this right here is the same equation as right here. And I'm going to call this stuff on the bottom A. Okay. What you could do is multiply top and the bottom by its conjugate of A. And so that's not supposed to be square root. Okay, I'll fix the solutions. All right, so I knew I didn't get 100%. So, but okay, so this is the complex conjugate. The denominator doesn't really matter, right? And as long as it's real, the reason the denominator doesn't matter when you do an angle, because you're taking a ratio of, if that's B and this is your A, taking the ratio, the denominators, they just cancel out. So these are the things that really matter right there. So if that's, in order for that to be 0, that means B has to be 0. And so that's how you're able to say, well, if B is 0, then that means that this stuff in here has to be 0. And that's how you find your RF. And for the frequency, set that equal to 1. And then you use this condition that you just found. So that's 0. That means it's just this over that. That's what this is. And then you just solve for what omega must be in order for that to be 1. I mean, yeah. Yeah, the reason I put the square root there is because I'm in habit just thinking about magnitude all the time. But that's not what's going on here. And this one is kind of the same. You have your magnitude of t being equal to 1, your angle being equal to 0. So since I only have like a couple of minutes left, I'll skip that. That's the same kind of problem. Schmidt trigger. Oh, I think I did make a mistake on the video where I said, well, let's replace this with a capacitor and a resistor. But that gives you an oscillator, and that's not what you're trying to do. I mean, it still solves the problem, right? But that's not really what you're trying to do. Yeah, you're not trying to make an oscillator. So anyway, so this is for you know, if the output was VCC, here's what VREF is. If the output was negative VE, that's what VREF is. So they're pretty much the same. And so in this case, if your input right here as a function of time goes in like that, once it crosses the VREF right here, then your output switches drastically back and forth as this signal goes back and forth across your VREF. After it gets over here, it's fine. But as it crosses VREF, that's where you get your crazy switching, okay? Yeah, but if you have your feedback right here with these guys, then this is separated, right? So even though it's noisy, once it crosses this, it'll stay there until it goes back over and crosses this one away over there. And that's the nice thing about that. So yeah, you could think of it as having some memory. This nodal analysis, I think that's self-explanatory. Or wait, does anyone have any questions about nodal analysis? Okay, cool. And the last couple of things, I think this is quite easy now. All you gotta do is make these short circuits, turn that to ground, and make that right here another short circuit, so it gets rid of that. Yes.
For the alpha loop now, would you also have RC in parallel with R3?
Yes. Yes. And I didn't do that. Thank you. Another point. That's probably like 5 points. Thank you. Yeah, so what he's talking about is that RC right there should be in parallel with that because that's ground. And I didn't do that over here. Okay, so yeah, very important point to make. So for B2, yeah, this is like the function generator. So you have your oscillator right here. So this is like your SMIT right here, but you're going to put your input as this RC part. That turns into an oscillator, and the output is this rectangular wave. You have your integrator. The output of that is a triangle, and then you have your filter, and that smooths the curves of your triangle. Yeah. Okay, so I will see you guys on Friday.